Thank you very much. This is now, in some sense, the main part of the whole series of talks here, because it's what got me started and what is my personal motivation to look at all these integral differential structures, Hölder-Baxter structures, etc. So it's about how you can use all this for treating linear boundary problems. Yeah? I'm not saying solving, because that's, so to say, only the optimal thing that can happen to you, that in some cases you may be able to write down something like an explicit solution. But even if not that, it's often interesting to do something else, yeah? To decompose it to smaller problems, for instance. Yeah? So you need some formal algebraic way of treating these linear boundary problems. Okay? And again, I want to start with a short overview of this talk, also giving credits. So this talk is split into three parts. The first is presenting a kind of abstract framework that tries to establish a notion of boundary problem in the absence of any differential or Hölder-Baxter algebra. So the first part is really just linear algebra, to tell you the plain truth. Yeah? But of course motivated by actual boundary problems with differential equations, etc. And it's based on two things. The first is an old result, an old paper that I wrote with Georg, that was mainly looking at the ODE case. It's actually a general framework, also including the PDE setting, but in some sense the results that are reported there are mainly useful in the ODE case. And we've extended that in this CAS paper to cover also the effects that you have with PDEs. The second part of the talk will now apply this abstract setting to the case where you have a differential structure and a Hölder-Baxter structure, so an integral differential structure, how you can then write down the Green's operators that we know to exist in some abstract sense, to actually have a computational representation in a suitable operator ring. The first result here was in a paper with Bruno and Engel, and that actually shows that the whole background of this is somehow unusual, because Engel, I assume most of you will not know him, he's an analyst working in inverse problems, ill-post problems. Has nothing to do with algebra, but for some reasons they were forced together in one boat on a joint project to see how algebra and analysis could be combined to get some new interesting things. And that was the nourishing ground for this whole symbolic boundary problem approach that came from it. Okay? So and this paper here is essentially a summary of my PhD thesis, which shows the status quo of the operator ring and the whole setting at that time. And the main formulation now is in the JSC paper and in this survey article in this book here, that's Proceedings Volume. Okay, and then in the third part, I'm going to look a bit more in detail to PDEs, what happens here, and that's just really work in progress, very much preliminary, but I think some interesting ideas are there that just have to be elaborated, and I'm grateful for any kind of inspiration that I can get from you guys here. Right, yeah. So let's just start with some classical example where all these terms like forcing function really have the natural meaning. If you look at the beam here, and we assume it's a thin beam in the sense that the longitudinal extension is very large compared to the lateral extension here. So essentially it's one-dimensional, mathematically speaking. And engineers, in the first approximation to describing this, like to assume that the cross-sections always remain plane. Yeah? So when this bends, obviously the cross-sections will also be bent, but the assumption is that it will still be orthogonal to the so-called neutral line. The neutral line is this line connecting all the centroid points of the cross-sections in the undeflected beam, and when it's deflected then it should still be always orthogonal to this neutral line. So that's the second assumption. Plane cross-sections. And then the parameters that you need to describe this is, of course, the elastic modulus, like in Hooke's law. It's just an extension of this idea. And geometric information, the moment of area. It's like an inertia moment, but here it's an area moment. And then for describing this, I take a coordinate here from 0 to 1, normalize it, that tells me where am I looking at this beam, which position. And what I want in the end is the deflection. So for instance, if I look here at position 0.2, then how many centimeters is it bent down? That's the deflection u of x. And what I'm given for computing this deflection is the distribution of loads. Okay? So I assume that there are some weights here, which could be because of the material itself. Maybe there's a heavier material in this part, some not so heavy material here. It could be because cars are going over the bridge or whatever. There's a certain distribution of weights at each point. That's this q of x. That's a forcing function. In this case, this is the forcing function. It literally describes the forces acting at each point. Okay? Then the physicists will tell you that this kind of setting is described by the so-called Euler-Bernoulli equation. It's the simplest approach. There are many more elaborate things like the Timoshenko beam, etc., that give corrections with higher orders. But here, in this setting, with these assumptions, it's just this kind of fourth-order differential equation. On the right-hand side, the inhomogeneity is this load distribution q of x, forcing function. The solution is u. But of course, for solving this, for getting the actual deflection, you will need some boundary conditions. And here, boundary conditions are really boundary conditions, okay? Because the boundary is the point 0 and the point 1. And typically, you will assume something like a simply supported boundary, which means that the beam can move, but it cannot move out of the position, okay? It can only rotate up and down. So, like here. So that's a simple support here. And mathematically, this comes out as the zeroth derivative, the function itself, and its second derivative vanishing. Okay? On the left-hand point, and if you have, here it's a different situation, if you have the same kind of angle, the wedge support here, then you have the same kind of boundary conditions on the point x equals 1. Okay? But you could also have other conditions. For instance, if it's a free end, like these trampolines for jumping, then you would have the third and the second derivative vanishing. And there are all kinds of mechanical conditions that correspond to certain boundary conditions here. Okay? We just pick any of these. Here, I think I pick the first case, that both ends are simply supported. And now, just to make things simple, I'm assuming also that the beam is homogeneous, so that I can pull out this E and I out of this derivative here, and then I just multiply it or divide it into the right-hand side, and I write then the resulting forcing function as f. So what I get is this kind of boundary problem. Fourth derivative of u, of the deflection, is equal to the given forcing function with these boundary conditions. And of course, you can use different boundary conditions if you describe a different scenario here. So that's a typical motivating example of what is called a two-point boundary problem, because there are just two boundary points here. And classically, the function space you would be using is here 4 times differentiable functions, but you can have more sophisticated spaces, Sobolev spaces, etc. But that is not my business here. Okay, so the analytical approach to this is, you would say, okay, there's a superposition principle here, and this superposition principle says that each of the forces at each of the points act independently, so that, for instance, the deflection at the point x, so this Roman x denotes the point at which we are looking to measure its deflection. So the deflection at this point x corresponding to a point load. So that means now at a different point psi, I have a certain load. Okay? Here's the point psi. So here I apply some load. And then I'm asking myself, how much does it bend at this point x? Okay? That's this kind of situation here. So the delta x, the Dirac delta, describes a point load at some specified position psi. Okay? So that's the deflection, the kind of elementary atomic deflection element. And then, since the superposition principle holds, you would expect that the total deflection of the whole beam should be a superposition of all these elementary deflections, but not just added, but added with a certain weight, because this u sub psi would describe the deflection resulting from a point mass. That means something like, you imagine there's one unit of weight. Think of 1 kilogram. It doesn't matter what the units are. But it's a unit. A unit weight, and then the total deflection would add up all these elementary deflections weighted by the actual weight that is applied at this point psi. Okay? So mathematically, what you get is an integral where this u sub psi of x is traditionally written as g of x and psi. That's the Green's function, and that is integrated against this forcing function f. Okay, so this g is really just this u psi of x. So the Green's function, the engineers will say, is the response of the system to an impulse, to a point force. Okay? And if you work it out, in this case, that's what you get. Typically, for these two-point boundary problems, the Green's function is not a smooth function. It is only continuous up to its, in this case, second derivative, but the third derivative will have a jump. It's always the n minus first derivative which has a jump. Here it's n equals 4. So now, what can we do with differential algebra here? Now the problem is that the differential equation itself is totally trivial. Fourth derivative of u equals 0. That's the homogeneous equation. We don't need differential algebra to work that out. So the question is, how can we understand what's going on here with the integration constants? What is the structure behind setting the integration constants in such a way that they correspond to the boundary conditions here, and how do they change? So what do we have to add? In this case, the differential equation is trivial, but of course the interesting case will then be if you have a complicated differential equation, then you can use some Galois theory, for instance, to describe closed forms of the antiderivatives, and at the same time there should be some algebraic machinery that takes care of putting the boundary conditions into the right integration constants. So that's what I want to suggest here. So the problem is, of course, that if you use differential algebra, then you would view the given function ring. So of course I'm aware that in differential algebra you wouldn't look at smooth functions because they have zero divisors, so you prefer holomorphic functions or something like that. But that doesn't matter here. So think of this as a differential ring. Then the problem is, what you have available as operations is the derivation, okay, satisfying these two axioms, and you have an algebraic representation for the analytic operation of a derivative, but there's no way in this structure to speak about u of 0 or u prime of 0. That's simply not part of the language. Okay? So what other algebraic structure can we detect on this object here that allows us to use something like u of 0 and u prime of 0 in a way that doesn't need topology? Of course, I want to stay algebraic in the sense of not needing any topological assumptions here. And the answer is point evaluations like u of 0, u prime of 0 here. The point evaluations algebraically are, and we had this already in the morning, they can be seen as multiplicative linear functionals. So in other words, characters. Algebra homomorphisms from F to the ground field K. So that's how we can encapsulate these evaluations. But of course, that wouldn't help by itself, because then this has to communicate in a suitable way with differential structure. They have to play together. There has to be some harmony here. And the trick is that you link it to the differential structure via the integral. And that's why the Rother-Baxter operator is so important already at this stage. It's also important when it comes to writing down the solutions, because that's an integral operator. But already here, it connects the differential structure to the evaluations. Okay? And what you see here already is that the evaluation, multiplicative linear functionals, are always intimately linked with integrals. So for me, these are two sides of one and the same story. Boundary problems and algebraic structures for integration, that's two things of the same, two sides of the same coin. Yeah? Okay, and that's what I want to encapsulate in the notion of the integral differential algebra. That will bring together point evaluations and derivation and integral. And the rest is not science, the rest is a linear algebra, how to actually handle then all these integration constants and bring them together in the right way. That when you forget when you abstract from this integral differential structure, then what is left is some linear algebra, and that's what I want to talk about first in this talk. Yeah? So this is very simple in this sense, just a linear algebra, but in infinite dimensional spaces. Yeah? That's the whole point. Yeah? Otherwise it would be trivial. Yeah? Okay, so let me start now with what I call abstract boundary problems. Abstract just meaning no differential structure, no Rothe-Wechsler structure, just the vector space. So what's an abstract boundary problem? I take two vector spaces, and you should think of f as smooth functions, or if you prefer, holomorphic functions. So these are some function spaces, okay? Vector spaces. Here just seen qua vector spaces. And then a boundary problem is simply a pair consisting of an epimorphism, okay, and an orthogonally closed subspace of the dual space. Okay, I will immediately tell you what that is. Huh? Think of the T here as a differential operator of any order, a linear differential operator. For instance, U4 prime, U prime 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 prime. That was the T before. The mapping that maps U to the fourth derivative. Okay? That's an epimorphism. And in general, a monic linear differential operator will always be surjective. So that's why here I assume that this is an epimorphism. And the other thing here, this subspace of the dual space, that's the boundary conditions. Okay? I view the boundary conditions as a vector space. As a vector space, as a subspace of the dual space, because each boundary condition, for instance, if you say u prime of 0 should be 0, now that describes a functional. The functional that takes u and maps it to u prime of 0. And that's a linear function. It's not multiplicative, but it's a linear functional, and therefore, if you take the linear span of all the boundary conditions that you have, you get a subspace. Okay? And this orthogonal closure, that's just a little technicality that is needed. And even in the abstract setting, I will just refer to the T as a differential operator, even though it's just a linear map. And I will refer to the B as the boundary space of the problem. Okay? Because in the applications, it will be the space spanned by the boundary conditions. Okay, so what I'm using here is a Galois connection between the subspaces of F and the subspaces of F star, okay? And actually only the orthogonally closed subspaces of F star. That's why I have a bar here, P bar. Yeah? It's also called the projective geometry. Yeah? So the projective geometry of a vector space is simply the collection of all its subspaces. Yeah? That's a lattice. Yeah? That's the complex, the orthogonal geometry. Yeah? And the Galois connection would just take a subspace of F, and I think of this A here, this subspace of F, as admissible functions. These are some functions that are in some sense admissible. I don't take all the C infinity functions, but a certain well-defined part of it that I call admissible functions. And then having these, I can ask myself, what conditions do they satisfy? In the sense, which linear functionals annihilate them? So that's very similar to what you do in algebraic geometry, where you have varieties and ideals. Just here it's linear. It's much simpler. It's also a Galois connection, an order reversing Galois connection, just the same here, just simpler. So the orthogonal of A is the conditions satisfied by A, and vice versa. If I have a subspace of F star, which I think of as a collection of boundary conditions, then I can simply look at the set of all admissible functions. What are the functions that respect the boundary conditions that I'm prescribing here? Okay? So that gives a Galois connection, order reversing Galois connection. And orthogonally closed simply means that if you start from a space of boundary conditions, you look at the admissible functions and then go back again and ask which conditions do they satisfy, normally you get more. Okay? But if you end up with the same, then that's called an orthogonally closed subspace in the literature. Okay? And if you restrict the right-hand side to these orthogonally closed subspaces, and that's the only ones that are really relevant for applications, then that's a bijection. The same thing in geometry. In geometry, what are the orthogonally closed objects? What do you think? If you have here ideals, so in geometry, on the right-hand side you would have ideals, on the left-hand side you would have varieties. So the orthogonally closed objects would be the radical ideals. Okay? Radical ideals. And there's no corresponding notion necessary here, because it turns out on the left-hand side everything is orthogonally closed. Yeah? They are always orthogonally closed, the subspaces of the primal space. Okay? So only on the right-hand side we need this notion of orthogonally closed subspaces. And I mean, to give you already an indication of what this means in practice, it means the following. If I take a Dirichlet problem, for instance, I take a square here, and I take some differential equation here. For instance, this Poisson equation, and I say that here, if you use coordinate system, here's x-axis, y-axis, and this would be, let's say, u of x and 1. And I set this to 0, okay? And similar here. Then, in addition to this condition, I will also get the condition that the derivative with respect to x is also 0, and lots of other differential consequences. And they will clearly not be in the span, in the linear span. Linearly, they are independent. So the orthogonal closure will automatically add all these consequences, but somehow in an abstract way, without mentioning the differential structure. Okay, so what you get here is then a modular lattice, simply because on the left-hand side this is already a modular lattice, so then on the right-hand side, since there's a bijection, it must also be a modular lattice, complemented modular lattice, and it's also complete, because if you take an arbitrary collection of these, you can always take the join and the meet. So get this lattice here. And in particular, any finite dimensional subspace of the dual is automatically orthogonally closed. Somehow very natural, because no differential consequences enter there. These effects come only for PDEs. So for ODEs, the notion of orthogonal closure is trivial. It's only needed for PDEs, because ODEs have only finitely many boundary conditions. Okay? So that's the notion of an abstract boundary problem. It's very important that this is clear, that this is the base. Now, having such a boundary problem, the most important notion is whether it's a regular boundary problem. And algebraically, I can describe this as saying that the kernel of T, which is the space of homogeneous solutions, must be a direct complement of the orthogonal of B. So the orthogonal of B, these are simply the functions that satisfy the boundary conditions. Okay? And then this just means that the corresponding boundary problem has a unique solution. You can simply work this out. This condition here is equivalent to the fact that when you write this now as a more or less a classical boundary problem, then it means that for every forcing function f, there's a unique solution u. Okay? So you see the differential operator that describes the differential equation, which is a linear inhomogeneous differential equation, whose inhomogeneity we regard as a parameter, f, and the boundary conditions here are in generally an infinite list of conditions. Even in the ODE case, if I have only one condition, u of 0 equals 0, then I have here infinitely many, because 2 times u of 0 is 0, 3 times u of 0, I take the whole linear span. So that's the conditions here. But of course it suffices to describe it on the basis. So that's regularity. And in fact, you can see that this direct sum has two parts. It means, first of all, that the intersection of these two summands is 0, and that corresponds to uniqueness. And it means, second, that the sum of B orthogonal and the kernel of T is the full space, and that means existence of solutions for every f. So if you have such a regular problem, then you can define the mapping that takes the forcing function f and maps it to the unique solution u. This is then well defined. And that's the famous Green's operator. But here it's much more general and abstract. Just for any abstract boundary problem, we have a notion of Green's operator. And in operator language, this solution here means that Tg is 1. So for instance, if you substitute for the u, gf, then you have here Tgf equals f, and that means TGF is equal to the identity operator applied to F. So since this is true for all F, it means that the operator TG is equal to the identity operator. And similarly for the boundary conditions. Yeah? Just means that the orthogonal of B, the space of all functions satisfying the conditions, that's the image of the Green's operator. Okay? And for a good reason, which I will give you tomorrow, I'm writing this Green's operator as the reciprocal of the abstract boundary problem TP. Okay? Why does this come here? Okay, yeah? So, one reason for writing this as TB to the minus 1 is that you can also multiply boundary problems, and that is actually the main reason why I'm considering the notion of boundary problem in isolation of all differential and Water-Baxter structures. Yeah? It's not only the natural love of mathematicians to do everything as abstractly and generally as possible. There's also a good reason here, pragmatically, because it covers at once the case of ODEs, PDEs, systems of ODEs, systems of PDEs, and in particular, this multiplication of boundary problems can be applied to the PDE case just as well as to the ODE case. Yeah? So what it does is, it takes the differential operators of the two problems, and what you would expect is just the product, the composition of them. But for the boundary conditions, it's a bit more involved. It takes the boundary conditions of the right factor as they are, but translates the boundary conditions of the left factor via the differential operator of the right. Okay? So it's somehow, if you have, for instance, if the T2 is a second derivative, then it will replace every occurrence of U in the boundary conditions here by U double prime. Yeah? So it somehow is natural because this will increase the order of the boundary conditions to the order of the product. Yeah? So it's a semi-direct product of the monoid of differential operators here and the abelian monoid of subspaces under addition of spaces. Okay. Okay, and it turns out, that's the reason for this multiplication, that if you multiply two regular boundary problems, then what you get is again a regular problem, and its Green's operator will be just the product of the two smaller Green's operators, except that the order is reversed. And that means, if you use the notation from before, the Green's operator of the product is the Green's operator of the right factor times the Green's operator of the left factor. Okay, so it's natural what you would expect, the so-called reverse order law. I will come back to that later tomorrow. And also the sum, which appears here in the definition, that is a direct sum. Okay, so, yeah. And that means, if you describe it more abstractly, that we actually have a category here whose objects are not just the spaces F, the vector space F, but so the objects are just the vector spaces, but the morphisms are not just the epimorphisms T themselves, but epimorphisms together with the boundary information B.
This B1 and B2 are subspaces of what? Can you show?
So they must be subspaces of F star. Yeah? So for simplicity, imagine that we have only one single vector space, F. Yeah? Then you can restrict all the operators to endomorphisms, and the only requirement is that they are surjective. Okay? And then the B1 will be a subspace of F star, and also B2 will be a subspace of F star.
That's not necessary to define your T2 star B1 plus B2?
What is necessary to define the...
This.
No, in general, you see, in general you have this situation. In general, the T2 can go to a different space. For instance, if you want to do analysis taking care of all the differential orders, then this can go from C3 to C1, if it's a second derivative, for instance. Yeah? And then it's just a matter of bookkeeping in which space you are. Yeah? You just take all those. So for instance here, yeah, if this B1 will be, so that belongs to T here, that will be a subspace of G star, okay? But then T2 star applied to this will give you a subspace of F, because that's the joint operator. So it fits together. You can then add it to B2, which is by definition also a subspace of F star, okay? So you get this category with morphisms being boundary problems, and the regular boundary problems are a subcategory. And as I said, yeah, if you consider just a single vector space F, a single function space, then you get a monoid. That's a category with one object, and a sub-monoid for the regular ones. Now, you can also define a notion of a dual problem, like in category theory, you always want to have duals, right? And essentially, this dual problem is just an embellishment of the Green's operator. Yeah? So what you do is, the G here, you should think of it as a Green's operator, but you add to it some missing information, namely the kernel of the differential operator from which it came. Yeah? But abstractly, I just do the opposite. Yeah? I say, here G must be a monomorphism instead of an epimorphism, and the S is a subspace of the primal space rather than the dual space, and regularity is characterized by a similar condition. And now you can define the Green's operator of the dual problem by these conditions, and as you would expect, you can also define a composition of dual problems, and you get two categories again, and then the association that I showed you before, that you take a boundary problem and compute its Green's operator. Now that's then just a functor between these two categories if you add this extra information, namely the kernel of T. And similarly here, you can also move back from a dual boundary problem to a primal normal boundary problem. You get an isomorphism or a dual isomorphism, an equivalence of categories. Okay? Good, yeah? So now, how do you actually determine Green's operators? And that's, of course, important for the Maple package also, and I will show you that tomorrow. What you can do is, if you can find a projector onto the kernel of T along the B orthogonal, yeah? You remember these two form a direct sum if it's a regular problem. And whenever you have two subspaces that are direct summons of each other, then there's a well-defined projector that whose image is B orthogonal and whose kernel is the kernel of T. So if you have such a projector, then you get the Green's operator by multiplying any right inverse of the differential operator with the complementary projector, 1 minus P. Okay? So the intuition about this is very simple. Yeah? The G here means you want to solve a boundary problem. Now the T diamond just needs to be any right inverse of T. Now, the easiest way to get the right inverse to a differential operator is to solve an initial value problem. Huh? You just, instead of the potentially complicated boundary conditions needed for the G, you just throw them away and take all initial conditions. U of 0 is 0, U prime of 0 is 0, U double prime of 0 is 0, as many as you need. Huh? So then you have a right inverse T diamond, which practically is much easier to compute. Also, if you do it numerically, it's much easier. And then you take, so if you imagine that this operates on a forcing function, yeah, then you get T diamond F being a solution of the initial value problem. And then this 1 minus P, so to say, twists your solution into a solution that also respects the boundary conditions. And so it somehow enforces the boundary conditions on your solution of the initial value problem without it ceasing to be a solution of the initial value problem. And there's a dual result for regular dual problems, of course. Yeah? And the important point is that in the ODE case, only in the ODE case, you can actually compute this projector explicitly. What you do is you take you can compute always in a relative sense. If from somewhere you have an explicit description of the kernel of T, which means solving a homogeneous linear differential equation. Yeah? So imagine you have fundamental solutions U1 to UN, and then, of course, you have a basis for the boundary space, because this is how the boundary problem is given in the first place. Yeah? It's only given in terms of a basis. Okay? So you have these two bases for the kernel of T and for the B. Then what you do is you form the so-called evaluation matrix. Okay? There's a big matrix whose rows are labeled by boundary conditions. Okay? So here is beta 1, etc. And the last row is beta n. And here in the columns you write the fundamental solution, and then in each entry you use the ith boundary condition and evaluate it on the jth fundamental solution. And that gives you the so-called evaluation matrix, and regularity of your boundary problem is exactly equivalent to the regularity of this evaluation matrix. And more than that, the projector is essentially the inverse of this evaluation matrix. Yeah? So what you do is, you take these boundary conditions, write them as a vector, beta 1 to beta n, a column vector, and take the fundamental solutions, write them as a row vector here, and then multiply them into this evaluation matrix, and you get the projector. Okay? And of course, there's a similar result for dual problems where you have the opposite situation. Okay, so practically speaking, of course, multiplication of boundary problems is not so attractive because it just makes the whole thing more complicated. Normally, you want to reduce the order of a differential equation and its boundary conditions. So it's important that we have a result that says that if you know how to factor your differential operator, and there are beautiful algorithms for this, like Van Hoey and Schwarz, etc., as in the ODE case as well as in the PDE case. Yeah? There are algorithms that for many, of course they cannot factor everything, but for many applications that come up in practice, they will often give you a factorization of the differential operator.
That's composition, right? T1, T2.
Yes, yeah. Multiplication, if you view, multiplication, I sometimes call it composition, sometimes multiplication, but... exactly. That's the multiplication in the Weil algebra, if you have polynomial coefficients, otherwise whatever else, Right, So the question is, if I have a factorization of the differential equation, can I use this to split the big boundary problem into two smaller ones? And that's important, of course, because it really means that you can use cascade integration. You integrate first the first equation along with its boundary conditions. Whatever forcing function comes in, it will produce some output solution, and this solution will be the forcing function of the next problem into which you feed it. So if this cascade process, and the result is that yes, this is always possible. You can always use a factorization here to get the factorization of the corresponding boundary problems. So in the regular boundary problems, the star just means it's a regular boundary problem. But the interesting thing is that the left and the right factor are very different from each other, because the right factor is essentially arbitrary. Because if you look here, the only condition on the right factor is that B2 is an orthogonally closed space, of course, otherwise this wouldn't be a boundary problem in the first place. And the second condition is that this must be a regular boundary problem again. So what is written here is equivalent to the fact that the B2 must just be a direct summand of the kernel of T2, or its orthogonal must be direct summand of the kernel of T2. On the other hand, the B1, here you have no choice at all, because if you look here, B1 is fully determined by B, but B is just the given boundary problem, the given boundary conditions. So it's determined by the given boundary conditions. K2 orthogonal, that's just the kernel of the differential operator T2. So we assume that this factorization is fixed. So if this factorization is fixed, and this is fixed, the B is fixed, H2 is any right inverse of T2. And again, we take, of course, as simple as possible one, like an initial value problem solver. And then this will be the B1. So this means no matter what you choose for your B2, and B2 can be essentially any subspace of B, you will always get the same B1. That's a very strange result. It just shows also that the definition of this semi-direct product is very asymmetric. It treats the factors very differently, and this comes out here by saying that the right-hand factor is more or less arbitrary, but the left-hand factor is unique. This is just determined by the factorization of the boundary problem. Okay? And actually, what you can do is you can write down explicitly the correspondence. If you choose a certain B2 here, such that this is a regular problem, as I said, that's the only restriction. But in some sense, that's the generic situation. You have to be really unlucky to choose a B2 which makes this into a singular problem. Generically, any B2 will be a regular problem. So any choice of B2 corresponds to a complement of the kernel here, and that's that describes exactly the kind of parametrization of these right-hand factors. Okay, So up to now, I've used the word boundary problem in some sense, in a very specific sense, because in the literature, in engineering, the word boundary problem is used for some other scenarios that are much related to this, but still a bit different. And I call these different incarnations. Yeah? I always think of a boundary problem abstractly just as a pair TB. But in a concrete form, it can look very differently. Because if this is a regular problem, then this means that a number of scenarios have a unique solution. The first one, which I showed you up to now, is what is called a semi-inhomogeneous boundary problem. Semi-inhomogeneous meaning it only has an inhomogeneity in the differential equation. But here, for the boundary conditions, I assumed homogeneous conditions. Yeah? So it's semi-inhomogeneous. In the literature, this operator G that takes the forcing function, maps it to U, this is sometimes called the signal operator in systems theory, or it could also be called the semi-inhomogeneous Green's operator. But actually, when you look into different papers, they will have different names. Yeah? There's no really unique terminology here, but it's important to keep the concepts distinct. So you can also do the opposite. Yeah? You can take a homogeneous differential equation and then use inhomogeneous boundary conditions. Yeah? So for each right-hand side, you have some boundary data here, and then but you get the notion of a semi-homogeneous Green's operator. Sometimes that's called the state operator. So it will take your boundary data B, which occurs here on the right-hand side, and map it to the corresponding solution. And again, that's the interesting thing. That is equivalent to regularity in the abstract sense. Yeah? So it also shows up here as unique solvability of this type of problem. You can also do both at once. Yeah? The fully inhomogeneous problem will have here an a forcing function and boundary data, and then what you map is a pair f and b, forcing function and boundary data to U. And again, this is uniquely solvable if and only if any of the others are uniquely solvable, and in particular, if and only if the generic boundary problem in the abstract sense is a regular problem. And then you might also ask, okay, then the fourth possibility is, of course, that I use 0 here, but that's uninteresting. Well, it's uninteresting only if we assume a regular boundary problem, okay? But tomorrow, in my last talk, I will also consider singular boundary problem, where this is not trivial at all, yeah? But only under this assumption. Yeah? This is trivial. Okay. So now here I have used the word boundary data in a slightly cavalier sense. Yeah? What actually is this here? What does this map into U here? And one way to formulate this is to introduce the following notion of boundary data. So first of all, it's clear that one and the same boundary problem can be described with different bases. Huh? So different beta i's will describe the same kind of boundary problem. Huh? And I call this a boundary basis. So the given boundary space is the linear span, but not only the linear span, is the orthogonal closure of the linear span of the beta I. Huh? So in the PDE case, it's a non-trivial extra step to take the orthogonal closure. So that's what I call a boundary base. And then I can introduce an algebraic notion of a trace map, which is something well known in analysis, where it needs some ingenuity from the topological side to understand which spaces you can use here, so that this is a reasonable continuous operator, etc. But here we don't have these complications. I just send a function f, in the sense of an element of the primal space, into a functional which evaluates any given beta here in my B. So this B is a subspace of the dual, so it consists of functionals. So it takes any such beta and evaluates the given f on it. Okay? So what I get is an element in f star. And then I can now make precise what do I mean by boundary data. By boundary data, I simply mean the image of this trace function. Okay? Because in general, this trace map here will not be a surjective function, because you may prescribe completely crazy boundary data that will not fit together into any function, because it will not be continuous, differentiable, or anything. So this here describes in a hidden way somehow the topological constraints. These are the boundary data that are actually accessible in your model in some sense. Okay, that's the image of the trace, and any element here is a legitimate collection of boundary data in an abstract way. And I distinguish between boundary data and boundary values. Boundary data are an abstract description of the boundary values. But if I want to get down to the actual numbers, what I have to do is I take a boundary basis, in the sense here, and then I take my boundary data and apply them on any element of the boundary basis. And then I get the mapping from I to k. So that's like a vector. It's just has infinitely many entries in general, but it's like a vector of values. So I have a situation similar to linear algebra. I have a basis-free description, abstract description. This is boundary data. And then after I choose a basis, I get something like coordinates. That's a component description in terms of boundary values. So that's the B bar associated with this boundary data. That's, of course, depends on the basis. And it turns out that this association is in some sense harmless because on the left-hand side, you don't have more information than on the right-hand side. There will always be exactly one set of boundary values that corresponds to a certain object of boundary data. So it's no more information, it's only more abstract here. The coordinates, so the basis is not distinguished here, but otherwise it has the same information. Okay, that's what this lemma says here. Okay, so now the next thing that I need to describe Green's operators in this more general setting, in the other incarnations, is what I call an interpolator. And again, that's just an abstract description of something very natural. It is just a right inverse, a section, a right inverse of the trace map. So the trace map encodes, of course, the information of B, which boundary conditions I choose. And then I write the B diamond for this section, right inverse. So the trace map goes from F to B prime. You remember B prime is just the subspace of F star, which is reached by the image of the trace. So that this is a surjective map. So then this has a section, and this section I call an interpolator. And of course, in general, there may be different interpolators. What does this mean practically? Well, practically, it means that here, in this model problem again, I may prescribe any boundary data here. So if I now use a non-homogeneous and inhomogeneous boundary problem, then on each side of this square here, I can give some function. For instance, I can say here this should be x squared. And then here, u of 1 comma y should be something, and it has to fit together, so it must be 1 here. So for instance, y cubed or whatever. So these are boundary data. And then the interpolator would take my boundary data, for instance, the x squared and the y cubed, etc. And what it has to do is, it has to give me a bivariate function that agrees on the boundary with the boundary values that I have specified. And that's what this means here. Just an interpolator. And of course, in practice, this boils down to interpolation by some kind of polynomials or other functions. Of course, like here, here I have chosen a boundary basis, the trivial one, which says that at each point I have a basis element. So if I have a boundary basis, then this just becomes a map from boundary values to the function space. And now it turns out that using this interpolator, which always exists abstractly, the question is only whether you can compute it. In terms of this interpolator, you can now describe also the other direction. If I have boundary values, how do I get the corresponding boundary data? And it's simply by using the interpolator like this. Because the interpolator will complete the boundary data to a function, to an element of f itself. And then you can evaluate it with any beta that you like. Because the beta here will be from a larger set of the orthogonal closure. And normally, initially, it's only given in terms of the basis itself. Whereas the other one has all these consequences, but in some sense, they are all contained in this B bar. Okay? Good, and now I can also write down the other parts of this Green's operator. So we have already had this one, the signal operator. Remember, that was just the right inverse of t, and this projector that enforces the boundary conditions. Now the state operator, H, this is the one which solves the semi-homogeneous problem. So here we are given just boundary data, but no forcing function. So how does it solve the problem? It takes an interpolator. So that gives something that just looks at the boundary values. It doesn't care about the differential equation. Yeah? It just produces a function satisfying the boundary conditions. And then the projector P will change it into a function that has the same boundary values, but in addition solves the differential equation. Okay? So that's what the projector does here. Somewhat dual to here, because here it's the boundary conditions that are enforced, whereas the differential equation was already satisfied, and here it's the boundary values that are satisfied, and the projector just makes sure that the differential equation is satisfied as well. And then the full Green's operator is, of course, just the sum of these two. Okay? Good, yeah? And in practice, of course, you would not use this formula because the computation of the projector P in a PDE is more complicated than solving the semi-homogeneous problem in the first place. Yeah? And then there's another approach that you can use, which essentially says that you get the boundary projector, you get the kernel projector from the state operator and the trace function. Yeah? So that's the other way around. Yeah? Given H, you can compute the P. And here you had H in terms of the kernel projector. Okay, so it's time for some examples, I suppose. Yeah? So here is, again, a kind of simplest scenario. I have here now a fully inhomogeneous problem of a simple sort, just the ODE. So here the forcing function is assumed to be a smooth function on the interval AB. A and B are the two boundary points. And here I have some condition. U of A plus U of B is equal to some number rho. So rho is just a real number. And U prime of B minus U of B is another number, sigma. Okay? So here the function space is, as I said, smooth functions on AB. The boundary space is here the span of the two conditions. One condition is L, that means evaluation on the left boundary point, so evaluation at A, plus R, evaluation at the right boundary point, yeah? L plus R, that's the left boundary condition. And similarly, RD minus R, that's the left-hand side of the second boundary condition. And the index set, yeah, before I said, yeah, boundary basis always is described with some index set. Here it's a very simple index set, it's just 1 and 2. That's the index set, okay? So the boundary basis is here, this here, yeah, that's the beta 1, that's the beta 2. The boundary data, in an abstract sense, is not the numbers rho and sigma, but it is the linear map that maps the evaluation L plus R to rho and the evaluation RD minus R to sigma, so that it's an element of the dual space of B. And of course, yeah, I have specified the effect of B on a basis. Yeah? The B is a linear span of these two, and therefore I have specified it on the whole space. Yeah? So that's the abstract description of the boundary data. And the boundary values are, as you would expect, the numbers rho and sigma here. And now you can see what happens. Yeah? If I change the boundary conditions, yeah? For instance, what do I do here? Yeah? I just add the two boundary conditions. I add this condition and that condition, then the U of B will cancel. So I get U of A plus U prime of B is equal to some other number, rho plus sigma, and I've just multiplied the other condition by minus 1, so U of B minus U prime of B is minus sigma. Yeah? And you see that, I mean, this other set of boundary conditions is just as natural as the first. Yeah? There's no reason why this is the right basis. Yeah? Any way of writing the boundary conditions is, from an abstract point of view, good as any other way. Yeah? So that's just a different basis. So what happens here is, I have a new boundary basis, gamma I, which is slightly different. Now the boundary data stays the same. It's just described in a different way, but it stays the same. But the boundary values, of course, they will change. It's now rho plus sigma and minus sigma. That's the new boundary values. Okay? So that's the ODE setting. Now in the PDE setting, a little bit more can happen. So I have here a simple Cauchy problem with the constant coefficients here. It's an initial value problem. Yeah? So I'm just prescribing the function at t equals 0. So if you think of t as the time, yeah, then at the start I'm prescribing the function u and its velocity. Its first derivative with respect to t. Okay? So that's the Cauchy problem here. And here, for some reason, I'm assuming holomorphic functions of 3, or in the case of the boundary conditions, 2 variables. Solution is again a trivariate holomorphic function. So that's the function space here. And the boundary space is now all these evaluations, okay? So I evaluate at 0 and x and y, where x and y are fixed real numbers. Yeah? Each choice of x and y will give me a different functional here. So I have here on the left-hand side infinitely many functionals, and I take the linear span and then the orthogonal closure of all these linear functionals. So the index set is here, R2, so that's the points x and y here, and another copy of R2 for the other choice of x and y. Okay? And the boundary basis is then just these operators here. I have, so to say, I have to index them with x, y, the first set of xy's and the second set of xy's. That's the boundary basis. And the boundary data, again, just associates to each element in the boundary basis the corresponding value here, f1 and f2. So the boundary values are f1 and f2 viewed as a map from I to R. And again, you can look at what happens when you change the basis. And here I'm doing something stupid. Huh? I'm taking the first boundary condition and I differentiate it with respect to x. Okay, so I get derivative of u with respect to x is equal to the derivative of f1 with respect to x. And since I'm doing this, I'm losing some integration constants, so I have to add some more information so that this stays equivalent. So for instance, I can prescribe what happens when x is equal to 0, and then I have to give for every value y the corresponding f1, yeah? f1 of 0 and y. Okay? So this problem here is equivalent to the other problem. In this case, the second formulation is somehow not as natural, of course. Yeah? It's much more economic to describe it with fewer boundary conditions like that. The problem is that in practice you often don't know that there's the simple description. Okay? But mathematically speaking, this is just as good as the other formulation. It describes exactly the same solutions. So the boundary space now would have these other functionals here, evaluation where t is 0 and x is 0 and y is arbitrary, and the derivatives here, and the other one stays the same. So now the index set is, I need one parameter here for this new family of boundary conditions, the y, and then a copy of xy here, and another copy of the xy's there. Okay? That's the new boundary basis, and if you use some labeling here, you can write it like this. And now the boundary data just has to map these elements here. Yeah? It stays the same, yeah? Only its basis description changes, but the object is the same. Whereas the boundary values are now different. Yeah? The boundary values are now given by 3 functions, one univariate and 2 bivariate functions. And in terms of the previous ones, they look like this. Yeah? So that's what is, so to say, the actual content behind this formulation of basis-free description in terms of boundary data on the one hand side and basis-dependent description in terms of boundary values on the other side. Okay, so that's just the linear algebra machinery that can be used to describe boundary problems in linear algebra setting. And now, of course, we want to do actual computations. And tomorrow, in my 4th talk, I will give you a little demo of the Maple package that shows how these computations look like. But now I just want to show you how this differential structure plays together with the linear algebra structure. So here's again just to recapitulate the definition of differential Rother-Baxter algebras. And now I'm using a slightly extended example, smooth functions on Rn. Okay? Because now I have, this should be indexed, yeah? I have more derivations and I also have more Rother-Baxter operators, and that's an example of a partial differential Rother, partial integral differential algebra if n is greater than 1. And I think I mentioned this already, so I won't go through this again. So also I mentioned this one. No, I didn't quite. Yeah. Yes. Yeah. This is just some other ways how you can characterize integral differential algebras. I mentioned the one with I mentioned this one in the morning, yeah, with this evaluation being a multiplicative projector. Yeah? And it's the same thing in mathematics. Whenever you have some foundational notion, it will have many different ways of description. Yeah? So for instance, another way that I haven't mentioned in